we're going to look at 24. 24 gives us two photoelectron spectra overlaid. And they say which element on the periodic table represents the blue line. Well, to know which one of these elements it is, we should probably label the orbitals. And remember, at this point, if you're struggling with labeling orbitals based on just using your periodic table, because you probably aren't going to have a filling diagram. If you don't remember the areas of the periodic table, then you might need to ask for some help about that. So that one right there is an S. So you remember that the first orbital, and we're just doing the blue one, is 1s, the second one is 2s, and both of those have 2 electrons. That's why they're that height. And if we've done the 1s and the 2s, we come down, the next one is the 2p, and there should be 6 electrons. That seems good. And then we come down after the 2p to the 3s, and there should be 2, and that makes me pretty comfortable because it's the same height as the 2s and the 1s. And then it looks to me like if this is 2 electrons, that one is 1 electron, and it's the next highest orbital, which would be the 3p1. So if that's the 3p, it looks to me like the blue one is aluminum. All right, the second one, it asks us what is the pink one. Sadly, I don't have a pink color, so we're going to go with red. This is the 1s, that's the 2s, that's the 2p, and this looks to me like the 3s, and it looks like 3s with 2 electrons because it's the same height as the other s. So 3s with 2, maybe magnesium? And then which peak on the blue element corresponds to the 3s? We've already labeled that, so I think it's pretty obvious. It looks like D. Why is the spectrum for the blue element shifted to the left? And this is probably the best question that we've had so far. It's really getting to the crux of your understanding of atomic theory, is if we've decided that we have aluminum, and aluminum its peaks are more to the left, well, think about what sort of the Bohr model of aluminum looks like. So here's aluminum, and has a nucleus, and in the middle of the nucleus of aluminum there are 13 protons, which I got from the atomic number. And you can see that it has these rings of electrons, right? There's the first ring, the second ring, like that, and it even has a third ring, kind of like that. And if we were going to think about magnesium in its nucleus has 12 protons, and it too has 3 rings, 1, 2, and then 3, kind of like that, 12 protons. So they say, why is the spectrum shifted to the left for the blue one? Well, the aluminum has 13 protons in its nucleus. That means it's all of its electrons, not just its external electrons. You can imagine its closest electrons, which are the 1s. Well, they're being held, I put it on the nucleus, let's go up there. The 13 protons is a higher effective nuclear charge, and so it will pull on those electrons and it will have higher binding energy. So definitely higher binding energy in aluminum. I'm going to label that higher binding energy so I don't get confused when I start looking at the questions. And it's due to higher effective nuclear charge, or more protons. Maybe they'll say more protons. The blue element, which was aluminum, right? Yep. The blue element has a higher effective nuclear charge, therefore holds onto its electrons tighter. Ooh, that sounds good. I like that one. The blue element is a larger atom. Actually, let's get into that while we're here. I think the first one's going to be the correct answer, but often debunking the others is really important. You know that magnesium, if I were going to draw it as an atom, it's quite a bit bigger than aluminum. Aluminum is a smaller atom. It really surprises people. Most people know that as you go down the periodic table, elements get bigger because they have more and more rings of electrons. But as you go to the right in every single period, the elements get smaller. And the reason is because they have the same number of energy levels, 1, 2, 3, 1, 2, 3, but as you go to the right, they get more and more protons. And so they pull those electrons that are on the outside, they get sucked in closer. So silicon has 14 protons. You can imagine if it had 14 protons in its nucleus and it still had 3 rings of electrons, those electrons out there would be pulled even harder and it would get smaller and smaller and smaller. So that's a good one to be thinking about. The blue element has a greater electron repulsion, therefore it takes less energy to remove electrons. Well, I will say the more electrons you have, the more electron-electron repulsion. It is true that it takes less energy. If they don't want to be near each other, you can imagine it's easier to convince them to leave. But does the blue element have greater electron-electron repulsion? Well, the blue one was aluminum, I believe. And let's see, it has one more electron out here. I think if I were going to do just the valence shell, magnesium would have 2 electrons in its valence shell. Aluminum would have 3. There is a little bit more electron-electron repulsion. But it would if that were the answer, it would take less energy to remove them, and you'd expect the blue peaks to be to the right. That sort of makes sense? In other words, this is a true statement, but the peaks would be the other way. The pink ones would be bound tighter, right? So that's why that's out. So I think the first one's the correct answer.